I want you to think about the sky not as empty space, but as a heavy, pressing weight. In the early 1950s, the de Havilland Comet was the first aircraft to truly conquer this environment, carrying passengers into the thin, freezing air of the stratosphere. It was a masterpiece of British engineering, sleek and silver, representing a future where the world was smaller and travel was effortless. But as I look back at the records, I see a fundamental misunderstanding of how metal behaves when it is forced to breathe. The Comet was designed to fly higher than any airliner before it, which required a pressurized cabin to keep people alive. At 35,000 feet, the air inside the plane pushes outward against the skin with immense force. Every single flight was a cycle of inflation and deflation. The evidence points toward a phenomenon we now call metal fatigue, but back then, it was a ghost in the machine. When we look at the fuselage of an aircraft, we see a thin shell of aluminum alloy. In the case of the Comet, this skin was remarkably thin, designed for lightness and speed. The issue wasn't just the pressure itself, it was where that pressure decided to gather. I want to draw your attention to the windows. On the original Comet, those windows were rectangular. They looked elegant, echoing the design of the trains and buses of the era. However, from an engineering perspective, a square opening in a pressurized vessel is a trap. If you follow the lines of stress moving through the metal skin, you find that they cannot flow smoothly around a sharp corner. Instead, they bunch up, they concentrate. The stress at the corner of a square window can be 3 or more times higher than the stress in the rest of the skin. Every time the plane climbed and the cabin pressurized, the metal at those corners was pulled and stretched far beyond its comfort zone. The industry at the time believed they understood the limits of their materials. They had conducted tests, applying pressure to a prototype fuselage thousands of times. They thought the structure was safe for 10,000 flights, but there was a missing angle in their logic. The testing was done on a single airframe that had been pre-stressed in a way that actually made the metal stronger than the production models. It was a false sense of security. In reality, the constant cycling was creating microscopic cracks at the rivet holes near those window corners. These cracks were invisible to the naked eye, hidden beneath the paint and the fasteners. They were tiny imperfections in the crystalline structure of the aluminum. With every flight, the crack would grow by a fraction of a millimeter. It was a slow, silent countdown. The mechanism of fatigue is a patient one. It doesn't require a massive overload to fail. It only requires the repeated application of a moderate load. Think of a paperclip. You can't pull it apart with your bare hands, but if you bend it back and forth enough times, it eventually snaps, with almost no effort. That is what was happening to the skin of the first jetliners. The system pressure to innovate and dominate the new jet age meant that these subtle material behaviors were overlooked in favor of traditional safety margins. The evidence boundary was reached when the Royal Aircraft Establishment decided to submerge an entire Comet in a giant water tank. By filling the cabin with water and pumping more water in and out, they could simulate the pressure cycles of hundreds of flights in a matter of days. After the equivalent of about 3,000 flights, the skin finally gave way. The failure originated exactly where the math suggested, at the corner of an opening. This realization changed everything. It taught us that we cannot just look at the average strength of a structure. We must look at the points of concentration. It's why every airliner you fly on today has rounded windows. Those curves allow the stress to flow around the opening like water around a smooth stone. We also learned about the importance of fail-safe design, where a crack in one part of the skin is stopped by a heavy structural frame before it can grow. The lesson of the Comet is that the materials we use have a memory. They remember every load, every stretch, and every flight. As engineers, our job is to respect that memory and design for the fatigue that time inevitably brings. If you find these deep dives into the hidden mechanics of history fascinating, please consider following for more case files. Your support allows me to keep exploring these stories of how we learned to build a safer world.